My name is Liba Duran, and I'm in charge of recording video for the project. Yeah, that's my job. Give me the camera back! Oh.
What's up? I'm Guy Sanchez, and I am the lead designer for this project. I also provided resources for the water bottle rocket.
Hi, my name is Diego Lopez, and we are building the water rocket project. Okay, I'm the assembly director, and thank you for shopping at Walmart.
Hey everybody, my name is Landon Rutton. I'm the chief engineer in charge of the engineering and simulation of this project.
And we're the guzzle juicers. For the next week, we're going to be building a water rocket so we can launch out in the back to see how far it would launch up in the air with the help of pressurized air. The launches will be starting on Tuesday, I believe. Things we can control about this are how much water we put in, how much PSI we apply, and how heavy the rocket will be. Things we can't control, however, are its altitude, its trajectory, and how long it'll be up in the air. However, if we can control just precisely how much water we put in, how much PSI we apply, and how heavy the rocket will be because of these changes, maybe it can go higher, its trajectory will be more stable, and depending, it could also stay up in the air some more time.
To start off, we didn't have the water bottle, so we cut off cardboard to make cardboard prototype fins.
This is a lot harder than it looks, guys.
Man, is that the best you can do?
No!
Once we cut out the cardboard, we started tracing and cutting out the fins so we could see if they work on the rocket.
Once we cut out one fin, we traced 3 more so we could put them on all sides of the rocket.
There we go. Give a little smile for the camera or a thumbs up. Yeah, there you go. There you go.
So once we realized that the prototype fins wouldn't work, we revised our design and made larger fins.
In the meantime, I got to taping up a cone that we scrapped later on due to weight issues.
And I was cutting out the final designs of the fins that we would end up using for the launch.
Once we were done cutting off all 4 fins, we cut off the top of 1 water bottle to put it on the bottom of our water rocket.
Careful, SpongeBob. Careful, SpongeBob.
Careful, SpongeBob! Shut up, Patrick! Shut up!
That's it?
At the end, this is our result.
So our hypothesis is that if we put more pressure into the water-filled, like registered trademark bottle rocket with as much water as possible, it will reach greater heights.
Once everything was said and done, we got to weighing it. I think it's gonna be like 260 or something.
260. Oh, that's too heavy.
Okay, that's too heavy, so it's like...
250. We can go
Wait.
255, yeah.
So, you said this is 250, right?
It's 250 right
But 260 is too heavy.
260 is too heavy.
So, we'll just say it's 255.
Hello everybody, my name is Markiplier, and today we're going to be launching this water bottle rocket right now because we can launch it into the sky, and as we're recording it, we're going to see how high it goes using the tracker program.
And with that, it was time to launch our rocket. Everything was going well up until this point. Until eventually it didn't. As is visible, the rocket did go off, but the camera was too shaky, rendering the video basically useless. And the second time we did record it, we hit a little bit of a snag. Thankfully though, Chris's team came in clutch, and they let us borrow the rocket. It isn't visible right away in the video just by looking at it, but if you zoom in just enough, you can see the rocket in the air. With this video, our friend Diego Lopez was able to use it on the Tracker app and get the results from it. The following videos are the results from this video.
Hi guys, my name is Diego Lopez. This is our rocket tracker video analysis edit. All right. So we have to look for. So some of the things that we have to measure and calculate is our time, displacement, potential energy, kinetic energy, momentum, acceleration, and velocity. All right. So let's start looking for our. So because we have our time and displacement all set, now we can look for our velocity. All right. From here on, so we first have to So in order to find our average velocity, we have to find our displacement, our change of displacement over time. Okay, and this gets us our 4.528 meters per second. If you convert that into miles per hour, that's about like 9.95 miles per hour. Okay. Now we have to look for our initial velocity and our final velocity. Okay. So this is our initial velocity. So 4.528 minus 0.823 times 5.498. So, and this gets us. This gets us 3,146 times 10 and negative 3. So that's about, well, if you count it backwards, this is what it'll get you. Okay, and this is our final velocity, which is 4.528 meters per second. Okay, so this is our first part from when it started to launch and it hit on top of the air while like stays on top of the air. All right. Now, if we look for part 2, where it has fallen down, where it started falling down, we have to look for our final velocity. We already have it. So because we need our initial velocity, time, and the acceleration and the time. Okay. So, in order to find all of that, we have to do is add these all together, and this got you 17.063 meters per second. This is our average velocity once it was on top of the air and heading straight down to the ground. Alright, next. Okay, so now we are looking for acceleration. So this is our acceleration in y value, and this is our time in seconds. You can see it's a bit weird, but it doesn't matter. Now, in order to find our acceleration, we need to find our change of velocity over change of time. So, because we found our change of velocity, it was 4.528 over 5.498. That gives us 0.823 meters per second. All right. And now, in order to find our deceleration, this is another way of writing it down, but I'm not explaining that part. Now, in order to find our deceleration, we need to find out. In order to solve it, is 4. So in order to solve it, you need to put our velocity plus our average acceleration times our time. Okay, so 4.528 plus 0.823 times 5.498. That gives us like about 9.052 meters per second. So this is our once it was going down from when it started up, going down, and that's
2, 1, go.
Hi guys, so this is again. Now we're going to be looking for our kinetic energy and our potential energy. So now this is the height, this is like that, and this is the time in seconds. Alright, now let's get it over to our. So now, in order to find our potential energy, it's pretty much very simple. You have to look for our mass, gravity, and height. So it's all written down, and this gets you to 38.595 joules. Now, in order to find our kinetic energy from going down up, so you have to put a half times the mass times like the velocity in square, and this will get you 1.325 meters per second. now it's already in the air. Now you have to convert the potential energy to kinetic energy. In order to do that, you have to put the 38.595 equals 1/2, and then times it by 0.155 grams, which is our rocket, how much our rocket weighs. You multiply that, and then you divide these numbers down, and then you have to put, once you get 498 equals v squared, now you have to square root it on both sides, and this will get you 22.31 meters per second. Well, if you're going down, it's like negative, right? So thank you.
Hello everybody, welcome to the momentum section of this video. Today we're going to be explaining the momentum behind our rocket. So here we have our graph representing our momentum. Now, before we get into any of the math here, I need to explain why the graph looks like this. In our graph, this is the initial momentum dropping after the initial launch by the rocket, and we have, some alternating momentum right here. It goes up and down as it's getting ready to go down back to the ground. And this section right here is very peculiar because it is the section where the rocket is actually heading down towards Earth. So it's reached the peak of its height and it heads back down and it steadily gains momentum, which explains this line right here. Now we're going to get into the math part of this. So we have two clear parts. We have the part where it is going up and rising, and we have the part where it is going down towards the Earth. Now for the part where it's rising and the part where it's coming down towards the Earth, we used a simple formula. We use P equals mass times average velocity. So with our math, we use the mass of the rocket, which is 155 grams, times the average velocity, which is 2.64, and then we smash those two together to get 0.951 Newton seconds. That is the measurement of our velocity, or our momentum. You don't have to put that up. And we do the same thing right here, 155 grams times a higher momentum, or our higher velocity, which is 10.795, and then we smash those two together to get 1.673 Newton seconds.